Okay, hello, Matthew here, and in this video, I'm going to be introducing us briefly to econometrics. Actually, econometrics the word econometrics was coined by one of the founding fathers of econometrics, Ragnar Fries, and he asserted that it was a combination of mathematics, economic theory, and statistics. Broadly speaking, econometrics gives empirical content on to economic relations for forecasting, decision making, testing economic theories, and policy evaluation. In 1954, Samuelson, Kopsman, and Stone defines econometrics as the quantitative analysis of actual economic data based on the concurrent development of theory and practice, related by appropriate methods of inference. In 1986, Aris Panos defined econometrics as a systematic study of actual economic phenomena using observed data. Now, the key ingredients in the definition of econometrics are economic theory, economic data, and statistical methods. Of course, the statistical methods like variance, covariance, coefficient of determination, analysis of variance, those are the tools, standard deviation, those are the statistical tools we use in the analysis of data. So in this video, we're going to be talking about a method of computing covariance and correlation coefficient. Now, at this point, I would like students to know that there's a difference between correlation and regression. Regression basically is a method of estimating or predicting the value of a dependent variable based on a known measurement of the value of an independent variable. Now, this is to say, once an independent variable is known, the dependent variable can be predicted from the value of the independent variable. So regression is more of predicting or estimating. On the other hand, correlation has to deal with the measurement of the relationship between two variables, okay? And we could have two or more variables. So measuring the relationship between two variables and getting a value which actually tells us about how these variables vary together is what correlation is all about. And we could have a strong correlation or a weak correlation. For example, when the value of the correlation coefficient is close to 1, it depicts a very strong correlation. So we have a simple example here. We're given a table that depicts the price of bread and milk. The price of bread is given as y, and that of milk is given as the price of bread is given as x, sorry, and that of milk is given as y. So we have these values for the price of bread and milk. Now, these are uh, related items. So we have, for us to do this, I'm going to be giving us a very simple, a well-known technique and a well-known formula for solving this. Now, looking at it, all we need to know is the variance of x and y and the mean of x and y. So I could add up, I could make this table this way. I could have an xy column, which simply means x times y, 50 times 10, 5 times 10, we have 50. This times this, we have 300. 15 times 5, we have 750. Okay, so we can also sum up this, sum up xy. When we sum up sy, we're going to have summation of x and y, we're going to have 1100. So the first thing we need to do is, in this question, we are required to compute variance. We're going to compute variance. And we are also going to compute the correlation coefficient. So we're going to look for the mean of x and the mean of y. So we have x bar is the mean of y, and then we're going to have summation of these items here, these values for y, for x. So this is going to be 5 plus 10 plus 15. We have three set of data points. We have three data points or three observations, 1, 2, 3. So this is over 3. And when you do this, you have 30 over 3, and that gives us 10. Similarly, we're going to calculate the variance of x var x. And the simple formula we're going to use is summation of x squared all over n minus x bar squared. Now, x bar is actually the mean of x, which is 10 in this case. So we'll also be needing a column x squared and y squared. So x squared is simply 5 times 5, which is 25. X squared is the square of this. 10 times 10, which is 100. And then 15 times 15, which is 225. And then y squared, we have 10 times 10, which is 100. 30 times 30, which is 900. And 50 times 50, which is 2,500. So this is what we have in our table. Now, summation of x squared means we are going to be adding what we have on this column. So we have summation of x squared will give us 25 plus 100 is 125 plus 225, and that gives us 350. Now, when we sum y squared, we're going to be having 100 plus 900, which is 1000, plus 2500, that's 3500. So this is what we have. So we're going to be calculating the variance of x now. We are ready. Summation of x squared is 350 divided by the number of observation 1, 2, 3. If we could have 5 in some cases, we have 10. So you count, this is 1, 2, 3. So we have 3 minus x bar, which is the mean of x. We have 10. So 10 squared is 100. And then we do this. When you divide this, you are going to have 16.67. Now, we're going to be calculating the mean of y, okay, which is denoted by y bar. And then we have the y values, 10, 30, and 50. So we add up this 10 plus 30 plus 50 all over 3. And that gives us 90 over 3, which is 30. So this is the mean of y. So similarly, we are going to be calculating the variance of y. You know, here we calculated the mean of x and the variance of x. So we also need to calculate the mean of y and the variance of y. So var y, variance of y. The formula for the variance of y is summation of y squared all over n minus y bar squared. So summation of y squared. So y squared, the summation of y squared gives us, we calculated here is 3,500 all over the number of data points observation 1, 2, 3 minus the mean, the square of bar y, we have 30 times 30, which is 900. So when we solve this, we have 266.76. Now, the next thing we're going to calculate is the covariance, because the question says we should compute covariance. So the covariance, cover of xy is going to be summation of xy all over n minus um, minus x bar, okay, y bar, okay. So this is the formula for the covariance x, y. So clearly you can see that the formula for the covariance x, y is actually similar to the formula for variance of y and variance of x. Now look at this. We have covariance xy, summation of xy all over n. Then here we have summation of y squared. Of course, y times y is y squared. And here we have, since we are looking for the summation, the covariance xy, it has to be summation of xy all over n. N remains the same, 3, because the number of observations we have is 3 actually. Now, here we have bar y squared, and here we have bar x times bar y. So we solve. Summation of xy, we have calculated this, and this is 1100 all over 3 minus the mean of x we calculated was 10, and the mean of y calculated is 30. So when you do this, we're going to be having 66.67. Okay, when you calculate this, 1100 divided by 3 and then minus 10 times 30 is 300, yes. Then when you subtract 300 from this, we have 66.67. So we have calculated the covariance. Now, the covariance gives us how the price of x and y varies with each other, But a more precise relationship between the price of bread and the price of milk is the correlation coefficient, which we are going to calculate. So to calculate for the correlation coefficient, we are going to be using the formula R equals to covariance of x, y all over the square root of variance of x times the square root of the variance of y. So we are set because we have already calculated the covariance of xy, which is 66.67. The variance of x has already been calculated from here, which is 16.67, and the variance of y have been calculated, which is 266.67. So we're going to have covariance xy is 66.67 all over the square root of the variance of x was calculated as 16.67, and the variance of y calculated as 266.67. And when you compute this, we're going to be having the square root of this 4.08 times 16.33, and that gives us 1.00065, and that's approximately 1. Now, from the value of correlation coefficient, which is denoted by 1, correlation coefficient is denoted by R, okay, not 1, R, we have the value as 1.00065. Now, when the correlation coefficient is 1, this depicts a very strong or a high linear correlation coefficient, which means the variables are actually strongly and closely related, because a correlation coefficient of 1 is a proof of a very high positive linear correlation between the two variables. Thanks for watching, and in the next video, we're going to be looking at the analysis of variance and other statistical methods. Thank you. Make sure to like, share, and subscribe to our channel, Learners Home. Have a good day.